Hey, welcome back to Fan Mama Physics. In this video, I'm going to do an example on interference. So, interference of two waves is going to depend largely on what their phases are at that particular point. So that is pretty much what we have to look into when we look at this question. So, by this time, hopefully you have some idea of how interference works, what does constructive interference means, what does destructive interference means, and how do you produce these interferences. In this question, we are going to do, it looks like destructive interference, but let's take a look at why. This one is going to be a little lengthy, so let's try it out. The diagram shows 2-point sources of sound, X and Y, so they're right here. Each source emits waves of wavelength 1.1 meters, that's our wavelength, and amplitude A. Over the distances shown, so here is one of them, any decrease in amplitude can be detected. The two sources vibrate in phase. Okay, that's important. So, meaning they do this, they vibrate in phase. Points and, okay, so, I think this is trying to say points O, it got cut off. Points O and P, so these two guys here, they are on the same line. That is 4 meters from the line collecting X and Y. So they're 4 meters away from these sound sources. Well, from the middle of those sound sources. O is opposite. O is opposite the... Oh, it definitely got cut off. I think what this question is trying to say is O is directly opposite of the midpoint. So it's exactly in the middle. So O is exactly in the middle, but on the opposite side. And then P is 0.75 meters away from O on that same line. We want to deduce that no sound is heard at P. So when we have no sound heard, it means that somehow when the waves interfere at P, they cancel out. When they cancel out, and you got it, is destructive interference. Destructive interference. And for destructive interference, you need the waves to basically be out of phase. So out of phase. Okay? So in order for that to happen is, imagine X and Y. These waves are going to come all the way here. Okay, and they're going to interfere. Since they are in phase, it means that if these two waves have exactly whole wavelength count, so if I count the waves, go 1, 2, 3, 4, 5, 6, 7. If I count say 5 wavelengths, and I count 5 maybe let's say that's a shorter distance, that's probably 4. If I count 4 wavelengths, so since they're in phase, imagine after 5 wavelengths. 1, 2, 3, 4. Actually, wait. First one's 4. So 1, 2, 3, 4. Okay. This guy's going to be here. And then this guy's going to go another wavelength. And then 5. Notice that they are in phase. And because they're in phase, you're going to get constructive interference. Which means we do not want whole wavelengths. We don't want this relationship here, the distance between the two, to be a factor of whole wavelengths. We need the opposite, which is half a wavelength difference. Because why? Let's say, imagine this wave went... no, let's not do that one. Let's say the bottom one traveled 4.5 wavelengths, and the top one traveled 5 wavelengths. So that's what it would look like. So let's say they start in the middle. Okay, so the first one would have gone... 1, 2, 3, 4, and then a half. Okay, so this guy's up here, and then this guy would have gone the whole 5 wavelength, and notice they're completely out of phase. So you need the whole thing, both the waves to have gone through the difference in the paths to be half a wavelength. So that's this relationship over here in this chart. So if you're in phase, you want the difference in the paths to be half a wavelength, okay? So that's what we're going to test for. We want X to P. We want the XP distance, the difference between XP and YP to be exactly half number of wavelengths. So to represent that, that's going to be m plus 1/2 of whatever wavelength we have, which is 1.1 meters. That comes in later. So to do that, we need to figure out what these distances are. And to do that, we're going to need a little bit of trig. So I'm going to set up a new paper and do some trig. Okay, so here I got a blown up diagram of this one again. So to do some trig here, I kind of have to figure out this distance here from x to p. That's going to make my right triangle, in which I know the base, which is, this is 1.6 from the middle. So let me just double check that. 1.6. Yeah, I have to assume that. Okay. So 1.6 is from here to there. I just have to add the 0.75 to get all the way down there. So what is that? That is 2.35. So this is 2.35 meters. And this whole distance here I know is 4 meters. And all I need to do is do a bit of trig, which my hypotenuse, this guy, is just going to be my square root of 2.35 meters squared. They're both in meters. That's fine. And 4 meters squared. So if I put that into my calculator, I get 4.639 in meters. I'm gonna save that for later. My second distance is from y to p, so that's this guy over here, this right triangle. Again, I have 4 meters as the height of my triangle. My base is going to be 1.6 minus 0.75 meters. Let me just see what that is. I'm too lazy to do the math. This is 0.85 meters. Okay, so that base here is 0.85 meters, which means the hypotenuse, to get the hypotenuse, I need to take 0.85 meters squared plus 4 meters squared. Okay, and that's gonna give me about 4.089 meters. Again, I'm gonna save this number. Okay, so now I have the relative distance. I have the distances from O to P, from Y to P and from X to P. Going back to this equation here, so I'm gonna put them in. So my XP is, sounds like Windows XP. I got 4.639 meters minus my YP is 4.0893 ... I'm just going to directly subtract it from one another. Okay, and that's going to give me 0.5499 ... So that's the difference between the two path lengths. So we're going to try to figure out whether that's going to be whole wavelengths or half wavelengths. M plus 1/2. And then our wavelength is over here. We know our wavelength. Our wavelength is 1.1 meters. So let's just go ahead and divide that on both sides. I kind of see my answer already, but we'll just do the whole thing. So divide by 1.1, okay, I'm going to get 0.5, is going to be m plus 1/2. And I'm just going to get rid of these brackets because I don't need them anymore. So I get m plus 1/2, okay? And voila! Hey, look at this. I got 0.5 plus 1/2 here. This cancels out. I get m is equal to 0. M is equal to 0. Okay? But m gives me a whole number. If m gives me a whole number, that means the difference between my path lengths is definitely half wavelengths. Okay? So you might be thinking, what? I'm so confused. Well, if you put it this way, when we subtracted the two paths, we got 0.54. If we divided that by the whole wavelength, we know that 0.54 is exactly half a wavelength. Because it's half a wavelength, meaning that the XP wave would have traveled exactly half a wave longer than the other one, meaning when they interfere at point P, they're going to be exactly out of phase. Because they're out of phase, it gives us destructive interference, and we just deduce that no sound is detected at P because our difference here was half a wavelength. You might be wondering, well, what if I get some other number? Like, let's say if I get, let's say the path difference is 1.5 instead. Actually, you know what? What is it? 1.5. Let's say you got something like 1.65. Okay, 1.65 as your path difference. It was not exactly half a wavelength, for example. Okay, so then that would mean that after you divide by 1.1, okay, then you're gonna get, what's 1.65 divided by 1.1? That's gonna give you 1.45. Oops, I did this wrong. So that's gonna give you 1.5 equals m plus 1/2. So if you take away half from both sides of your equation, so that's gonna minus 0.5, minus 0.5, that gets rid of that. You're gonna be left with 1 is equal to m. And that's a whole number. So your path difference is again by half a wavelength. So what does m mean? M is kind of like an order. It's like how many extra waves have passed by. So for example, in if the path difference was exactly half a wavelength, then I have one wave traveling, one path would have been, say, 5 wavelengths. The other one would have traveled the path of, say, 4.5 wavelengths. If I have the order of 1, it means my first wave would have traveled an extra wavelength, so they would have differed by 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths. So that's what this m is all about. It just tells you how many more wavelengths have passed by. But it doesn't matter how many more wavelengths have passed by. As long as the difference between the two paths are either by whole or by half wavelengths, then you'll have either constructive or destructive interference. Okay? So this is a classic, is a good example just to get your juices flowing, especially when you have no sound detected. Phew, hopefully this video wasn't too long, but hopefully you got something out of that. So hopefully it made a little bit more sense for you to do some questions later on. I thank you for watching Fan Mom Physics, signing out.